and then over to you.
Okay, so hi, I'm a master student from Germany, and yeah, it's a funny coincidence because today we are looking at the Stern-Gerlach experiment, and both were physicists in Germany, which is quite a nice coincidence. And yeah, so I'm doing my master's like in quantum physics, quantum computing, and so yeah, that's why I'm a student assistant here. Yeah, so I think that's everything for me. Do you have any questions regarding the homework?
Do folks have specific questions, or maybe even if you want to start with just a refresher on Stern-Gerlach and some of the key takeaways, and that might inspire questions.
Yeah, of course. So I'm gonna share my screen with my tablet. So now you should see my whiteboard.
Yeah, we can see it.
And yeah, so this week we did the Stern-Gerlach experiment. So you see, I pronounce it like the German way, which was an experiment these two physicists did. And there they found that the atoms they put into this experiment have another property they didn't know before, which is now called spin. So therefore they had like some sort of, I think it was silver atoms they shot like through some magnetic field. For example, when you have here the North Pole and here the South Pole. So they shot it through this magnetic field, and they saw that they had like two different points where the atoms went. And so because it was silver atoms they put in, they have like more or less the same properties like electrons do. So for the spin properties, we know now, but they are neutral atoms. So they don't have like any charge, which if they had charge, there would be another problem, because when you have like charge in a magnetic field, you get like some force which uh, uh, acts onto this electron or onto this charged particle. So this is why they did it with silver atoms, because they are like neutral, they don't have any charge. And yeah, so from this experiment, they saw that the spin, which is like sort of the intrinsic angular momentum of the particles, is like quantized. So you have like this h bar half and minus h bar half. And this is like one of the biggest sort of how I have to see how to formulate this. So one of the biggest things in quantum mechanics, because you have like this quantized steps. You don't have like a discrete sort of vector which goes, but you have like this quantized properties of the quantum mechanical particles. And yeah, so this was like a big thing for quantum mechanics and for all the people who doubted that quantum mechanics was a thing. Yeah, so in principle, this was this experiment. And yeah, so I told you why they did it with the silver atoms. And yeah, so you can also, so you did this too, you can also like measure this in the different bases. So as I drew it here, you would have like the Z bases, because you have like, if you look like from front, so if you look like this, you have here north and here south, but you could also do it. So this is like the Z basis direction, so because you're looking in Z direction, but you could also do it in X direction, where you might have like Z and north, sorry, north and south in another way. And this is the X direction. So you have to work with this two bases. And I think this is something we did already. So you might know, so I'm gonna delete this. So I mean, like, you might know that we have like this block ball. We have like when you have Z, you have this direction and this direction. And for X, which is like this, you have the plus and the minus state. Where plus is a superposition of 0 and 1. With a plus, and minus is the same with a minus. And this is something you have to consider when you solve like this week's homework problems. So are there any questions yet?
Are you able to see the chat? Just
Yeah.
Okay.
So somebody wrote a silver atom can form both plus and minus cations. Yeah, but like you don't you don't put the ions in there, you put the neutral atoms in there, so they don't have any charge, and but they have spin. Okay, so if there are no other questions for this, I think I'm gonna just show the homework and talk a bit about it. So there was the question, is spin a real thing like we understand, or is it an imaginary thing? So I don't know what you mean, like as we understand. So yeah, of course, spin is a real thing. You can see it in this experiment, but like all quantum properties, it's hard like to grasp. It's nothing you can like see with your eyes or like look at. So at a moment you just have to see like spin as a property of some atom or electron.
I think so. She followed up with, is the electron really spinning? So maybe helping us understand, like, spin is kind of a hard word for it because everyone thinks like spinning like a
Yeah.
ball.
Yeah, so no, it's not like that, it's like moving around. So so it's misleading to like see the electron as a small spinning object. So like if you're doing like quantum physics, you just have to simply accept that the electron, that the spin is just like this intrinsic angular momentum this electron has. And yeah, because like because like if you would look at it as a spinning object, you would have like some sort of paradoxes, because unlike, for example, a ball who's spinning, the spin of an electron can't change. So stays the same, and it has only two possible orientations, whereas like for a spinning ball, for example, it can have more orientations. And so it's like in quantum mechanics, so even the thought of thinking that like electrons and protons and so on are like some sort of solid objects that can rotate in space, it's like difficult to say, because you like had it before that like you can't really say the electron is like this really uh, confined object. So you can't really think about it as like in analogy to a ball who is spinning. So it's just something you have to more or less accept, that it's a property of like quantum mechanical particles, like the electron, and like you just have more or less to accept it, that it's like charge, or like yeah. Yeah, so it's different from the spin we know in the non-quantum world. So you just have to like, it's just property of a quantum mechanical object. Okay, are there any more questions?
I think showing the homework would be great if you want to walk through some of the problems with your awesome background.
Yeah, okay, so I think I share my other screen for this.
There, we can see it.
Okay, good. So I have to see my chat again. So okay. Yeah. So the first one was which of the following properties of an electron is measured in the Stern-Gerlach experiment? So I mean, like we were talking about it more or less the whole time. It is spin, and yeah, I mean, like the Stern-Gerlach experiment was the experiment where these both physicists like discovered that there is something like spin, and that it's not like a discrete spin, but that it's like that it's not a like continuous spin, but that it's discrete. So you have like two points in your experiment at the end. So when you look at the end, where you like measure your silver atoms, you have like two lines. Okay, so the right answer is of course spin. The second one is, after passing through a Stern-Gerlach apparatus, how many possible values for electron spin can be measured? So, I mean, I told the answer, like right now it's two. This was like the big the big discovery they made with this experiment. The third one is, the orientation of the Stern-Gerlach apparatus corresponds to which of the following? So the orientation of the Stern-Gerlach apparatus, this was something I told you like before. Can I comment on this? No, I can't. Okay, so this was like, if you put it like this, you like more or less measuring in the set basis, or if you like put it on the plane. So I try to draw it like this. So here now you're on the x-axis. So this is the x-axis, and there you are like in the plus or minus basis. So the right answer is A. So the orientation, how we put the apparatus, shows us the basis, or we are measuring in different bases. Okay, now we have a few true or false statements. So, the first one is a quantum state is changed when it's measured. So this is true. This is something like, which is sort of a big problem for some experiments we do in quantum mechanics, but also a big advantage for something like quantum key distribution, which we need for quantum cryptography. So if someone finally like discovers a good algorithm to factorizing primes, this might come handy for us. So when we measure a quantum state, we collapse its wave function. So I'm not sure if you had this yet in the course, and then sort of the quantum state changes. So this is true. The next one is the probability of measuring a given quantum state does not depend on the basis of measurement. This is false because, of course, it depends on the basis. So if you want to measure a zero state in a different basis, it's a different probability if I do it like in this x basis, or if I do it in the computational basis and the set basis. So this one is false. And the sixth one, electron spin is an example of a single level system. So this is something, so what is a single level system, or what is like in the opposite, like for example, a 2 or a 3 level system. So this means like you can put your state in two different, like, so a 2 level system is you can put your state in two different ways. For example, like for our charge, like plus or minus one, or here our spin, of course, is a 2 level system because it can be minus h bar half or plus h bar half. So this is also false. Okay, and now we have like this sketches of the results of the Stern-Gallach experiments. And so here the Stern-Gallach apparatus is represented sort of by this box. And of course, you get the output of the spins measured in the 0 and the 1 basis, in the 0 and the 1 state. And of course, as you knew from the lecture, it should be like half-half. So this is why you can see also that this is a 2-level system, because it can be in state 1 or in state 0. And of course, you could do it also, as I said, in a different direction. So instead of like putting it like this, you can put it like this. So I hope you can see it. So one time you have like the North Pole. So my middle finger is the North Pole. You can have it like this and put a shoot like the atoms like this. And one time you can put it like this. And of course, this corresponds to different bases. And so the other one is the x directions, where the base states are plus and minus. and they illustrate it like this. And now the question is like, how do different combinations of this measurements affect an initial electron beam? And yeah, so the answers, which is important. So I had one question today in the student office hours. So because it's the answers are like 1% of the initial number of electrons. So you have like to think like if we had 100% electrons go in, and what percentage of those electrons you can like measure at the end. Okay, so the first one is this here. And here you have like 2 times 2 Stern-Gerlach experiments like after each other, both in the set basis. So the answer of the question in number 7 is like, what percent of the initial number of electrons will travel down branch A, and the other one is like branch B. So, and here what you have to think about, okay, what happens like at each step of this apparatus. So if you look at the first one, so I hope I can, or I will do it with text. So, okay, it works. Okay, if you look at the first one, of course, you know, okay, when I put an electron beam through my Stern-Gerlach apparatus in set basis, I get like half of them, of the electrons in state 1 and half of them in state 0. So I get here like 50%, and I get here 50%. Now I put like these 50% of my, okay, so I will put here 100%. So I will put like half of my electrons I like put into this dot, so I just don't use anymore. So I have only like half of my electrons left after the first apparatus. Now I put them into the second one. And what happens there? So I have like all of my electrons in state 1. So what happens? All of them, of course, all these 50% are in state 1. So state 1 after the second one will be 50%. So it's still 50%, and here it will be 0. Because all of them here, you only take the one in the one state into the second Stern-Gerlach apparatus, and of course there, because spin is like their intrinsic property, this doesn't change anymore, and it will still be 50% there. So now you can more or less like read the answer. So for A it's 50%, and for 8 it's 0. So was there a question, I think? Okay, so why 0? So okay, again, I think I will draw this. So let me put this away and show this again. Okay, so you had like this set A, B. Okay, so you get 100% of the electrons. So here you have like still all the electrons left. You put them into, and then you know, like from the Stern-Gerlach experiment. So here when you have like north, oops, south, you put them here, and then like on the in the end you see like you can measure like two ones, 1 and 1 and 1 and 0. And so you know that here you get like 50% for 1 and you get 50% for 0. And then you put like only these 50% into the next apparatus. So you only put like 50% of the initial electrons here, and they are already in the one basis because you only put like this one in the next Stern-Gerlach experiment. So here again, north, south. And then of course they have the spin. It's the intrinsic like property of them, so it doesn't change anymore. So of course they will only get like to 1. And so you get here 50% again for 1, and for 0 you get 0%. Yeah, so no, it's not 50 and 50 because like you already like singled out the up-pointing spins. So it will still be like pointing up, and that's why the second Stern-Gerlach apparatus doesn't really change the spin. So it does not change the spin, but you can see like we only have like spins pointing up. Did this answer the question? Okay, so I think I will just draw the next one here. Why for 1 it's not 100? Yeah, because it's called, so of course, like if you would say, okay, this 50% are my 100, of course, then you would get like in the second one you get like 100% of the ones you put in, but you want to know how many percent of the initial electrons you get at the end. So if you would think of it in numbers, so it's not the way like this, but if you would think of it in numbers, so if you say I could count my electrons, you could say, okay, I have here 100 electrons, then I get like 50 here, 50 there, and then of these 50 I only have 50 here, and then you can like look it up. So it's not, so if you compare like this 50 to the 100, it's like 50% of the initial ones, so not 100%. So this is why I like highlighted, I try to highlight this in the question. So you have to think of like what percentage of the initial number of electrons do you have at the end. So the next one is this one. So again, here you have 1, here the 0, oops. It's the 0 state you again like put out, and then you put the X like this. And there, first of all, like you have to look, okay, what is more or less, so I will draw it again. So for, okay, it's hard to draw. So now this here is my set basis. So I go like this. So I get like 0, which is spin up, or 1, which is spin down. So at the end. And then I can do it like in X direction. So I have like my north and south. And there I get like plus, which is more or less spin right. So this is something which I have to write like in apostrophes, because this is just something you could think of it, but it's not that mathematically correct. And you can have minus, which is like more or less the other way around. And yeah, so there you have to like think about like how can I write my plus and my minus. This is something I did before. So plus was 0 plus 1 over square root half over square root over 2 of 2, and minus was 1 minus 0 minus 1 over the square root of 2. And like with this, now we can solve the homework. And yeah, so first we have to think about, so we're putting 100% of the electrons in. And then, of course, we know that it will be half in spin up and half in spin down. And for the plus and minus, so you're putting like half of this spin up states into the X one, and there, you know, like, okay, I have this spin up in both of them, like here and here. I have like a part of it is spin up, part of the superposition. And this means, okay, in both of plus and minus states, I have this one state. So I can also, like, of this 50%, half of them go in the plus state and half of them go to the minus state, or half of them are in the plus state and half of them are in the minus state. So this means like half of 50% is 25%. So the solution is like you get like 1/4 of the initial electrons will end up in C and 1/4 will end up in D. Was this clear? So I got a question, is there any basis of atomic properties that supports the outcome that the electrons will be evenly distributed in the experiment? So what do you mean with this? So I mean, like, if you have the Stern-Gerlach experiment, you have like the even distribution of the so if you like have one Stern-Gerlach apparatus, you have like an even distribution of electrons, because half of them like in mean have spin up and half of them have spin down. Yeah, so it's a bit abstract, but it's just like a bit like quantum mechanics is, because you can't really grasp it because it's so small. But for me, this is something why I really love quantum mechanics, because it's so abstract, it's so small, but it works. And it's like, it's sort of crazy, but also sort of surprising. And yeah, that's why I really love quantum mechanics. So the question is like, why 50-50 and not 30-70? So this is something like as I said, the spin is sort of the property of this angular momentum, and you can have either spin up or spin down, and like how do I say this? So you only have like these two values, and like in mean you have like half of all the electrons in plus and half of the electrons in minus. This is just like how it is. So like I don't know if this was done in the lecture, so I will put this away here, and then I can show you like what is the difference in to the classical like model. So if you had like if you look as it would be classical, you would have like a continuous sort of magnetic moment of your in the field. So if you say like, okay, this is my z-axis, and you have like this magnetic moment, so like this is sort of a ball. And if you had like this magnetic moment, if you would be in a classical way of manner, you could have like values like everywhere on this ball. So it would be continuous. So classical. But what this Stern-Gerlach experiment saw is that you only have like this two sort of values where you can like project to 1/2 and -1/2. So this experiment like more or less demonstrated that you only have these two values, which we know now as spin. Okay, so I have to think about it. So that it's like 1/2 is and that you only have like this two is a result of the experiment. I have to think about it. So first of all, okay, before they did this Stern-Gerlach experiment, there was another experiment of Peter Debye and Sommerfeld, I think, where they looked at another physical property, and there they like sort of found out that there should be some sort of like discrete property of atoms, and then like the Stern and Gerlach did this experiment, and they like found out that it's some sort of intrinsic magnetic moment which has like this quantization. So I think there was no, so as far as I know, that there was no theory before. So because they were quite surprised, at least that there is a spin of the magnetic, so a spin of the quantum mechanical particles, and that it's like half, so half valued. And I think this was something they got surprised. But yeah, because of this very important experiment, we know now that electrons have a spin and that it's discrete, so it can be either 1/2 or -1/2. And like always, when you like write a wave function, you can, so this is something which is a bit more like theory, you always write the spin as a property of this particle in it. So this is really something which is like one monumental number that is very important for quantum mechanics. So this is why we do this experiment, and we like teach this experiment, because it was like a huge deal then that they sort of found out that there is this property called spin. Does it justify that the atom will remain neutral? So what exactly do you know, do you mean with this? So I mean, like, as I said, electrons can have spin, but they are not neutral. But for this experiment, you need like neutral atoms, because as you might know from some sort of middle or high school physics class, there's something called Lorentz force, which happens when you have like a charged particle in a magnetic field. This particle can feel some sort of force, which puts it in some sort of direction. And this is something you don't want with this experiment, because it could like jinx your outcome. So you want to have like a neutral atom into to like shoot into this experiment. And they use silver atoms because so this is sort of a bit chemistry, or I don't know. So because silver atoms have like the number of electrons and atoms that they like sort of act similar to a single electron, but they are still neutral because they have the same, because they are like atoms and not ions, but they have the more or less same properties as electrons. Okay, are there any more questions? Otherwise, I would go on with the exercises. So we had like the ZX, and now the last one was, oops, that you had like an Stein-Gerlach experiment in X spaces, then one in Z, and again one in X. And I will write here again. So here we have plus. We discard the -1. Here we have 1, which we discard. Then we have 0. Then we have plus and -1. Plus and minus. And now the question is, what happens in E and F? How many % of the initial ones do we have left? So again, we put in like all of our electrons we have in our beam. And then we have like the first Stein-Gerlach experiment in the X basis where it's either plus or minus. So you get 50% of the beam will be in the plus state and 50% will be in the minus state. So 50% will more or less be spin left and 50% spin right. Okay, now we only put like this 50% plus into the set. And now we have to think about, okay, what is this plus? So as I wrote before, it's 0 plus 1 over square root over 2. So if you look here, so this plus consists of equal parts of 0 and equal parts of 1. So this plus is like 50% 0 and 50% 1. So here we put in 50% of our initial electrons. So we get like here 25% and here 25%, because like 50%, as I said, are of this plus are 1 and 50% are 0. So, okay, after the second one, now we have like only 1/4 left. And now we put it again in a Stern-Gerlach experiment in X spaces. And here we have to think about, okay, what happens now? So now we have like the 0 set state, so our electrons. So we singled out all electrons which had spin down, and now we put it in an experiment where we measure if spin is left or spin is right. And now, because we had spin down, we know, okay, our plus is this and our minus is this. And in both of them, we have like spin down. So both of these are a linear combination of spin up and spin down. So again, if we put in a spin down into our, so spin down electrons in our Stern-Gerlach experiment in the X basis, we get like that 50% of them go into the spin left state and 50% of them go into the spin right state. So again, we have like 50% of 25, which is 12.5, so 1/8. So yeah, this is like how you would do it a bit more like mathematically, how to look at these basis states, how they look. But you could also think, as I did it like in my explanation. So after this, you have either spin left or spin right. So I will do it like this. Yeah, okay, no, later, before I did it like this. So spin left or spin right. And then you want to have like, you do a Stern-Gerlach experiment like in this direction, so in Z direction. And now you know that, yeah, okay, if I look at it in Z direction, so it's like a combination of spin up and spin down. So these are like combinations of spin up and spin down with some sort of factor. So there I always get like, because I have like equal parts of up and down, that's why I get right. So if you like sort of look at vectors in a coordinate system, if I have a vector up and a vector down and I add them, I get like left or right, depending on if I how I add them or if I subtract them. Okay, so now I have the spin up and spin down. I know that now I have like half of them, half of the, like, for example, right, go into spin up, half of them go into spin down. And now I have to look again in the X basis, and I put like my spin down here in it. And I want to see which one is like right and which one is left. And there I can sort of, I always also have to think about, okay, how do I get like right and left from up and down? So, okay, it's always like I have this down this. I need a down vector to construct the right vector, and I need a down vector to construct the left vector. So this down vector will also like split the number of like the atoms I put in will also split like in 50%. So always here you get like this 50% splitting. That's why like at the end you only have like 1/8 left. Yeah, so the north magnet is positioned right. So yeah, so you have here north. Yeah, yeah. And the other question was, is this because Z magnet changes the left right spin to 50-50 again? Yeah, so you have the right spin. So you are like in this plus state. And you know that this plus state like consists of an equal amount of up states and an equal amount of down states. This is like what this tells you. You don't have a vector, so you don't have something like 2 times 0 plus 1. So this is not the case. So you only have like 0 plus 1. So you know you have from both, you have like equal amounts. So you know that it's 50% 0 and 50% 1. And you sort of have to multiply them like all together. Question 1 and 2, please. So, okay, yeah, so yeah, this is like depends on in what basis you measure. So yeah, so electron has spin up or spin down if you like measure in Z basis. But if you like measure in X basis, you can't say one in 0 you have like this plus and this minus state. So there you have like sort of spin left and spin right, but they are like combinations of spin up and spin down. This is why you always like see this two measurement outcomes depending on what basis you measure. So another question now was, why is Stern-Gerlach experiment important to quantum computing? So of course, to like understand quantum computing, you have to like get a grasp a bit of like what happens in quantum mechanics, what is this quantum everyone talks about. And I mean, like, it's called quantum computing, so you need a bit of like understanding for quantum mechanics. And Stern-Gerlach experiment is a very important experiment, as I said, for quantum mechanics. And this is why it's good to know this experiment. And like sort of this is like one of the most basic two-level systems you can have, like because you have like spin up or spin down. This is a two-level system, and like for qubits you also want to have a two-level system. And so this is like sort of one of the most basic two-level systems you can have. And so we know this because of this Stern-Gerlach experiment. And I mean, like, as I said, it's nice before learning quantum to have some like ideas how quantum mechanics works, or at least how it evolved. So so why did we go, so why do we now know now like the principles of quantum computing? How did we get there? And this is quite nice, I think, to see. Spin up and spin down as like wax on, wax off by Mr. Miyagi experiment. I think I don't know this experiment. So I can try to. So it's from Karate Kid or something. I don't know. So I think this was sort of like a funny question. Yeah. So it's like just a property the particles have. So are there any more questions? So as I said, it's quite nice to look into these concepts to understand quantum mechanics, and this is something I really like about it, because this experiment like really showed that there must be something quantum, and like that you can't look at a continuous world anymore, but you have to look like at discrete levels. You're welcome. Thanks for coming. How do you call the X and Z? So these are different bases you can measure. So Z has a special name. It's called computational basis because it's like the easiest one to measure in. But they are just sort of like bases of your system you can measure in. Yeah, they are. So in the Bloch theory, you can like visualize these bases. So let me draw it again. So I found. Now it's a bit more nicer. So if you have here the Bloch sphere, you can have like Z direction, you can have X direction, and then you also can have Y direction. So yeah, I will do the Y too. And then you can like measure in this different bases. So in Z you have either 0 or 1. In X you have like plus or minus, and in Y they are called R and L. But this is like more or less. So here we only do the Z and X one, because like in the Y you have an imaginary number too. So you can, for the Stern-Gerlach experiment, you only have like Z and X, because there you can really like put your apparatus, so place your apparatus to measure in these two bases. And so one doing like this and one doing, one doing it like this and the other one doing it. So you have like, I hope you can see it, so like this, and then putting it to there, and then can like go like this or either go like this. Okay, some people want to see 9 and 10 one more time. Yeah, I can do it again. So, of course. Okay, 9 and 10. So this was Z, X. Okay, so I will write two states we have as outcomes in our Stern-Gerlach experiments. So here the question was like, what percentage of the initial number of electrons will we have at C and D? And so this means like at the beginning we have 100%. And then like we want to see what happens. So you know from the oops, now it's gone. Wait. You know from the Stern-Gerlach experiment that when you like put an electron beam into this apparatus in the Z basis, so it looks like this. So you have like north pole up here, south pole up here, or other way around, doesn't matter. You get like one half of them in the one state and one half of them in the zero state. So oops, you have like, sorry, one half of the electrons you like just put away, and you only put like one half of the initial electrons into the next Stern-Gerlach apparatus in the X basis. So which is like, so the first one is like this, where you have like here Z, and okay, I try to do it. So you have it here, and then you put like half of them away. So you put like these, you put away, and then these you take in another apparatus, which now is like in X direction. So this should be like in X direction, so on the plane. And now you want to look what happens here in C and what happens here in D. And okay, so here we have to look at, so what is plus? Plus is like sort of the spin right. So it's called spin right, but yeah. And this means you have a combination of 0 and 1 with a plus, and minus is the same with a minus. And from there you can see, so we have like spin up left. And if you put spin up into like this Stern-Gerlach apparatus, you see like we have this one in both of them. So in the plus and in the minus one. So this means like we have in both of them, we have this up spin. And in both of them we need it. And this means like equal parts of these 50% go into plus and equal parts go into minus. So 50% times 50% gives me 25%. So I get at the end 1/4 in C and 1/4 in D of my initial electron beam. And 50% I just like put away. So are there any more questions? Thank you. So it's quite an interesting topic. It's a bit hard to grasp because it's like nothing we experience in our daily lives, but it's like a very fundamental property of quantum mechanics, and it's like really interesting, I think. Thank you. So
If
you're
there's no
welcome.
more questions, we can wrap up early. It's totally up to you. Some folks
Yes.
also, if you want to say anything about your research or some of your work, I know students sometimes enjoy that, but we can also just wrap when people are done.
Yeah, so if somebody wants to stay, I can tell you a bit about it. So yeah, I have to say in my bachelor thesis, I sort of did something with spin. So you can go very deep into spin, and it's quite nice because like spin in a solid state sort of can behave also like a wave. So like all of our different spins can behave like a wave, and it's called magnon, so like a magnetic excitation. Um, and this is something I did in my bachelor thesis. So how this magnetic excitation interacts with light, which is quite interesting because maybe like this magnons or like this sort of solid state property can interact with photons of some sort of um, like mm, how do I call it, like some sort of hardware drive for quantum computers. So if you have a quantum computer which is based like on photonic devices, this could sort of like work as something where you could save your excitations. So this is quite nice. This is like why what I did more or less with spins, because they also can like form these waves. And the thing I do now is like more what we do in this course. So now I'm doing a variational algorithm for a physics model in quantum computing. So yeah, this is something we might do at the end of the course. How old I am? 24. Like a spin capacitor. Yeah, sort of like a photon battery. Like where you can sort of store your photons and then like store your excitations you had before, and then like if you want like try to compute with it anymore. But yeah, I'm not sure if this is like the, so this is something we said, okay, this could happen. This like was our drive for doing this research project. But like the most quantum computers nowadays are like made with superconducting qubits. So for them, this is like not practical or not um, good at all. So we can't use it there. What do they mean when they say fidelity? Yeah, so fidelity means like how good the expectations were. Um, so it's a bit like you need a bit more quantum mechanics to sort of explain this, but like fidelity more or less means like how successful was this process. So I can see if I find some nice. Yeah, so yeah, if you say like in a state fidelity, like you can say how more or less how successful you were in like producing the state. So how close more or less is it to the state? Yeah, this is something you can calculate. And yeah, it's quite nice to see how successful you were like with your simulations or with your experiments. Yeah, of course. I mean, like if you are in the real world and not doing just a theory, you have like, of course, a lot of losses, decoherences, and so on. So, I mean, like this is also a problem of quantum devices nowadays, because you have a lot of losses and yeah, so you really you can't say like the state you want is, you don't have the state like in a clear way. So it's just like you want to get as close as possible to the state. Mm, somebody asked about a proof for the 50-50 distribution. So like this is an intrinsic property. So spin is just like a property that each quantum mechanical particle has. Okay, are there any more questions? Because I don't want to like dig in too deep, because I think the things I'm doing are a bit more theoretical and you need a bit more physics to it, or a bit more like quantum theory to it. So I don't want to dive in too deep, because I know you will learn a few things in this course, and the other things, yeah, are just something you have to learn.
How about this? What got you interested in quantum computing?
So I mean, like first I was really interested in quantum mechanics. I really love the beauty and sort of the craziness about it. I think there was one really famous physicist. I don't know who said it, but like if you think you understood quantum mechanics, you're wrong. And this is something I really like, because you always learn new aspects of this like theory, and it's quite nice because you can't grasp it like in the real world. Like um, you can't just like grab an electron or an atom, and this is why I really like quantum mechanics, and I also like the algebraic beauty of it. And so I this is why I wanted to go into like, or this is why I wanted to do something with quantum mechanics. And this led me like to my bachelor thesis. And after this, I was like, okay, I really like how quantum computers evolve, and like how you could use them to solve like problems we physicists have now. um, you might solve them in a few years, and I like wanted to be a part of it, or want to understand how to like do or build like this quantum computer, or how to like develop algorithms for it to like solve problems we have now, and how we can tackle them later. And it's like sort of theoretical what I'm doing, but I know that it might have an application, and this is what I like about it. So it's not like that I'm sitting in my high tower and doing some calculations, but I know that this might be like a little grain of sand in the bucket to make some new model, or to solve some new model. Um, Now there was a question, is there any reason silver atoms were used for this experiment? Yeah, so I explained it before. So oops. If you have like this two magnet configuration, if you would put in a charged particle, you would get a Lorentz force. It's called, is something you might have done in some undergrad or middle school, or I don't know what it's called in other countries, physics course. So if a charged particle goes, so charged particle plus magnetic field high means that we get a Lorentz force. So, and this is something we don't want to have in this experiment, because we don't want to like measure sort of the charge, but we want to measure the spin. So we need a neutral atom, and there we use the silver atom. And the silver atom, so I have to look the atomic number. So it's 74, and it more or less means, like, if I would draw it like this, we have 74 protons and 74 electrons, which are like all in this sort of shells around the core. And like you only have like at the outer shell, you only have like one electron, which is like single there. And this is like the electron, which spin property more or less you measure in this experiment. This is why we use they use silver atoms. What's the main career path after this course to take to become a quantum computer scientist? So I'm no expert in this field. I just studied physics because I really liked physics. So, but I mean, like, as you can see with your TAs, there are some that studied like computer science. Some they studied physics. Some studied math, I think. So you have like equal chances when you study computer science and physics, I think. So it's not that you have to like study like this one subject, I think. So I also think Peter Shor with a famous algorithm is a mathematical. So yeah, there are various directions you can do. So I studied physics, or I am studying physics. So in Germany we don't have like majors. We have like only like one subject we choose, except we want to go in teaching or education, then you can have like more. But I studied physics because I really liked it, and yeah, and I think it was the right choice. You're welcome.
Cool. Should we wrap up there?
Yeah, I think we can like end.
Perfect. Well, thank you so much. I think, yeah, everyone's feedback says what I need to say. You incredibly clear, and I think hopefully folks are leaving with a great understanding. So, and I'm so glad it was for Stern Garlock, and you can say it way better than I can.
Yeah, I feel like quite strange because everyone here in the course says Stern Gerlach or something, but I mean I have the German pronunciation, and then it always sounds like this really funny, I think. But I mean, like, they were called Stern and Gerlach.
You're saying it the correct way, so we can learn from you. Awesome. Well, I hope everyone has a great weekend, and we will see you on Sunday during lecture. Cool. Thanks so much. Bye bye.
Bye.